So welcome back. In the very first lecture of this module, we have been introducing the method of canonical ensemble formalism, and we have seen that the fundamental aim in canonical ensemble formalism is to find out a relation between the probability PR that a system is found in a particular microstate or eigenstate with energy ER. So the relation between PR and ER is so crucial that from the knowledge of this probability PR, we will be able to get an idea about the thermodynamics of the system. So we begin our discussion on how to find out the relation between the probability PR and the energy ER, the energy eigenstate ER of a particular system. As we have discussed in the previous lecture, we can have or we can adopt two approaches. One of such approach is to regard the system to be in equilibrium with a heat reservoir at a common temperature T, and then study the statistics of the energy exchange that happens between the system and the reservoir. Means we are going to study the equilibrium between a system and the reservoir. So this is the first approach. In this lecture, we will be just following the first approach. The second approach will be discussed as a separate video. Now here you consider a system. We are considering a system A. System is labeled as A, which is immersed in a very large heat reservoir A dash. So this is the system, and this one is the reservoir. So we call them respectively as A and A dash. So let's say that we are considering the equilibrium between the system and reservoir. The systems in canonical ensemble, any system in canonical ensemble is characterized by the macrostate N, V and T. Means the temperature of the system should be maintained constant. In order to maintain the temperature constant, the system is allowed to exchange energy. So we can see here both the system and the surrounding has achieved the same temperature. That is why we say that the system is in equilibrium with the reservoir, right? So since both of them have got the same temperature, we can understand that the energy exchange is permitted between the system and the surrounding. It means that the system at any given instant of time can have energy that is varying from some 0 to E. The energy can vary from 0 to E, some fixed energy E, where the energy E will be the sum of ER, the energy that is possessed by the system at any instant, and what ER prime. So we can say that the total energy of the system can vary between 0 and E, and the total energy of the system and the reservoir put together will be equal to, we can say that ER at any given instant, let ER be the energy of the system and ER prime will be the energy of the surrounding. But see, ER and ER prime should be equal to say E naught. Let's call that this is equal to E naught, that is a constant. So the total energy of the system plus surrounding is taken to be a constant. And there is a condition that compared to the energy of the surrounding, which is ER prime, or compared to the total energy of the system plus surrounding, the value of ER is very, very small. So I can say that ER by E naught. ER is the energy of the system, okay, which is a very small part of the entire universe, So ER by E naught will be very, very small, right? and that is pretty easily understood, because you know that reservoir is assumed to be having very large heat capacity, and it the energy of the reservoir is of course going to be very, very large, right? So now what we are going to do, that if at any time t, so what is this ER and ER prime? ER and ER prime are the energies, okay, possessed by the system as well as the reservoir at any given time. That is okay, ER and ER prime. Now basically in see the statistical, or basically in the statistical method of thermodynamics, our fundamental aim is to calculate what is known as the number of microstates. So let me introduce some symbols here. Let omega prime, remember I'm using primed quantities for reservoirs and unprimed quantities for what? The system, and quantity raised to 0 for denoting the entire combination of system and reservoir. So let me denote, let omega prime, which will be a function of, this omegas, the total number of accessible microstates for any system, will be a function of its energy usually. So omega prime, which depends on ER prime. So I have written omega prime, a function of ER prime, let it represent the number of states of the reservoir. So I am writing reservoir is represented by A prime with energy, number of states of the reservoir with energy say ER prime. Okay, now you know that larger this number, okay, larger the value of this omega prime, or larger the number of states available to the reservoir, larger will be the probability of the reservoir attaining that particular energy ER prime. That was our very fundamental concept of statistical mechanics. Hope you remember, we have seen that if which macro state will be having highest probability. We had concluded from our throwing two dice experiment that if any particular macro state is having large number of microstates, then that macro state will be the one having highest value of probability. So as such, we can just conclude that the larger the number of states available to the reservoir, we are talking in terms of the reservoir in place of the system, remember. So the larger the number of states available to the reservoir, means larger the value of this omega prime, larger will be the probability of the reservoir to attain that particular energy ER prime. Correct? Okay. Reservoir accessible ആയിട്ടുള്ള സ്റ്റേറ്റുകളുടെ എണ്ണം കൂടുതലാവുകയാണ് എന്ന് പറഞ്ഞാൽ ഒമേഗ പ്രൈം കൂടുതലാവുകയാണ് എന്നർത്ഥം. ഒമേഗ പ്രൈം ആവുകയാണ് എങ്കിൽ അതിൻ്റെ അർത്ഥം എന്താണ്? നമ്മുടെ റിസർവോയർ, നമ്മൾ ഫോക്കസ് ചെയ്യുന്ന റിസർവോയർ ആ ER പ്രൈം എന്ന് പറയുന്ന ഒരു പർട്ടിക്കുലർ എനർജി സ്വീകരിക്കാനുള്ള, അല്ലെ പർട്ടിക്കുലർ എനർജിയിൽ കാണപ്പെടുവാനുള്ള സാധ്യത കൂടുതലാണെന്നാണ്. ഇനി ER പ്രൈം എന്ന് പറഞ്ഞ ഒരു എനർജി റിസർവോയറിന് കിട്ടുകയാണെങ്കിൽ അതിൻ്റെ അർത്ഥം സിസ്റ്റത്തിന് ഏത് എനർജി കിട്ടിയിട്ടുണ്ടാവും? E0 മൈനസ് ER പ്രൈം ആയ ER എന്ന് പറഞ്ഞ എനർജി കിട്ടിയിട്ടുണ്ടാവും. അപ്പോൾ നമ്മളിവിടെ എന്താ ചെയ്യുന്നത് വെച്ചാൽ, സിസ്റ്റത്തിന് എനർജി ER കിട്ടുന്നതിൻ്റെ കണ്ടീഷൻ പറയുന്നതിന് പകരം നമ്മൾ എന്ത് ചെയ്യുന്നു? റിസർവോയറിന് ER പ്രൈം എന്ന് പറയുന്ന ഒരു എനർജി കിട്ടാനുള്ള സാധ്യതയെ പറ്റി നമ്മളിപ്പോൾ പ്രതിപാദിക്കുന്നു എന്നേ ഉള്ളൂ. സോ ബോത്ത് ആർ ഇക്വിവാലന്റ്. കാരണം എന്താണ്? ER പ്ലസ് ER പ്രൈം ഈസ് ഈക്വൽ ടു E0 ആണല്ലോ. E0 ഈസ് എ കോൺസ്റ്റന്റ്. അപ്പം സിസ്റ്റത്തിന് ഫോർ എക്സാമ്പിൾ ഇറ്റ് ജസ്റ്റ് ലൈക്ക് ഐ ആം റൈറ്റിംഗ് 98 plus say that or 98 plus 2 is equal to 100. Suppose that I am just taking some equation like, and let's say that 98 is ER prime and this 2 is what? Just say ER, and this 100 is E0, like something like that. Okay, I can write like this. So the meaning is that 98 റിസർവോയറിന്റെ 98 എന്നുള്ള ഒരു വാല്യൂ കിട്ടുക എന്ന് പറഞ്ഞാൽ അതിന്റെ അർത്ഥം എന്താണ്? The answer is that it is corresponding to the saying, equivalent to saying that the system is getting an value equal to 2. കാരണം എന്താണ്? Total is equal to 100. ഇനി റിസർവോയറിന് 90 എന്നുള്ള ഒരു വാല്യൂ ആണെങ്കിൽ കിട്ടുന്നതിൻ്റെ പ്രോബബിലിറ്റി പഠിക്കുകയാണെങ്കിൽ തീർച്ചയായിട്ടും എന്തായിരിക്കും, ദാറ്റ് ഈസ് ഇക്വാലൻ ടു സെയിങ് ദാറ്റ് ദ സിസ്റ്റം ഈസ് ഗെറ്റിംഗ് 10 ബിക്കോസ് ദ ടോട്ടൽ ഈസ് റിമൈനിങ് എ കോൺസ്റ്റന്റ്. അപ്പോൾ നമ്മൾ ഇവിടെ ചെയ്യാൻ പോകുന്നത് റിസർവോയറിന്റെ ടേംസിലാണ്. എന്തുകൊണ്ടാണ് റിസർവോയറിന്റെ ടേംസ് ചെയ്യുക എന്നുള്ളത്, ഇറ്റ് ഈസ് ഓൺലി ഫോർ മാത്തമാറ്റിക്കൽ കൺവീനിയൻസ് ദാറ്റ് വി ആർ ഗോയിങ് ടു സീ വിത്തിൻ എ ഫ്യൂ മിനിറ്റ്സ്. ഓക്കെ, അപ്പോൾ ഓർക്കുക, greater the number of states that is accessible to a reservoir with energy ER prime, larger will be the probability of the reservoir attaining that particular energy ER prime. Okay, or correspondingly the system attaining the energy ER. Now that is I can say the probability. So this is a very important thing, that is the probability. I'm writing PR. See that I'm not writing PR prime, I'm writing PR. What is PR? PR is the probability that the system attains a microstate. The system attains a microstate having energy ER. Okay, so instead of writing ER, expressing the probability in terms of ER, I am writing the probability in terms of what? ER prime. So I am writing PR is proportional to omega prime. That is a very important turning point. Omega prime ER prime. Omega prime ER prime. So you have to keep in mind that omega prime ER prime will be the number of states of reservoir with energy ER prime, but greater the number of states of the reservoir, greater will be correspondingly the number of states of what the system also, because they are of course they are directly proportional. If there are a large number of ways in which a reservoir can exist, of course there will be large number of ways in which what the system also can occur. Okay, so I can say PR is proportional to omega prime. So it is equivalent to writing PR is proportional to omega of omega of ER or omega prime of ER prime, because both of them will be directly related. And I can rewrite, okay, so that is a very important thing, that is I can rewrite this omega prime ER prime can be just equated with omega prime. Instead of ER prime, I can use equation number 1. What is ER prime? Can you write ER prime as what? E naught. ER prime can be written as E naught. So this is ER, E naught minus ER, E naught minus ER. Now you can understand that now see, even though we have taken omega prime, okay, the number of microstates accessible to the reservoir, finally it is related to the energy ER of the system. Okay, that is why we are just following this particular technique. Moreover, it is mathematically convenient when you make an expansion that you are going to see. So this is let me say this is my second equation to just with. Now you know that so we have made an assumption, not an assumption, it's a reality, that the energy of the system will be very very small compared to the energy of the reservoir or the total energy, right? That is so okay, due to that reason, so I can write since ER is the energy of the state at a particular instant t, is very much small, it is negligible compared to the total energy of the system and the reservoir in total. What we can do that now, this is a function, you can see that is a function, and this function omega prime is a function. This function can be Taylor expanded. You know, that is a proper proper situation for doing the Taylor expansion for a function, right? You know, we are doing the Taylor expansion for a system, or the Taylor series expansion for a function f of x around some particular point, say x equal to a, whenever that a is lying very close to that particular thing x, right? Okay, so similarly, so what we are going to do here is that we may Taylor expand. We may Taylor expand means we can expand that function as a Taylor series around the value say that just ER prime is equal to E naught. We may Taylor expand. Which function? The function is omega prime. Taylor expand omega prime ER prime, omega prime ER prime around the value around the value, I'm writing it explicitly, ER prime is equal to E naught. ER prime equal to E naught. What is the meaning around the value ER prime equal to E naught? Always refer to equation number 1 here. Okay, when ER prime equal to E naught, see, means when these two are very near, it means that ER is very small. It means that ER is tending to 0, right? ER is very small, right? That is around. So when I say that I am expanding it around ER prime equal to E naught, what we mean here is that is ER is equal to, that is around ER equal to 0. So we are expanding the function around ER equal to 0. And one more thing before we go for the expansion, you know that this quantity omega or omega prime is going to be very large. Okay, because you know that is the number of accessible microstate of a system in the thermodynamic limit, having n number of particles, where n is of the order of Avogadro number. And we have seen that when the system is statistically large, okay, the total number of accessible microstate is going to be pretty large. It will be of the order of minimum Avogadro number. So since omega is large, that is also one more idea that we are using. Since omega or omega prime, whatever it is, both are large. Omega prime is very large. Okay, instead of expanding this omega prime as a series, we will be expanding its logarithm. So instead of expanding omega prime as a series, I'll be expanding log of omega prime is expanded. Log of omega prime is expanded. And why do we do it like this? Only because, okay, then we will be having a series expansion which can get converged. Okay, so it is only for convenience or for mathematical convergence. For convergence, you know what is the advantage of taking logarithm of bigger quantities? You know, for example, log of 1 is equal to 0. You know, log of 10 is equal to 1. Log of 100 is equal to 2. Okay, log of 1000 is 3, and so on. So you know that even the 1 and 10 vary by 10 levels. The value is between log 1 and log 2 is what? Only 1. Okay, so like log 10 is 1, log 100 is what? 2. The difference between 10 and 100 is 90, but you know the difference between 1 and 2 is only 1, right? Similarly, log 100 and log 1000, you can see that 100 and 1000 vary by 900 units, but the value of their logarithm, they are actually they are just varying only still by 1. So it means that when you take logarithm of a big number, that number converges to a small number which you can easily handle. Okay, and that is the mathematical convenience of taking logarithm. And maybe you remember, okay, you are doing this one practically. I don't know whether I have discussed about this one. Yeah, okay, in your practical electronics practical classes, you are supposed to draw what is known as the frequency response curve of a amplifier. You say a C amplifier, you are just drawing the frequency response curve. What are the quantities that you take on the axis? Of course, on the y-axis it is the voltage gain, right? Voltage gain of the amplifier is taken along the y-axis. And what you are supposed to take along the x-axis? Actually, you are supposed to take the frequency of the signal along the x-axis. Frequency of the input signal along the x-axis. And you know, you using your signal generator, you are varying the frequency from very low values, like say that say 10 hertz, to say that you are varying up to some, say, 20 megahertz. So hertz to megahertz, a very long range of frequency you are applying to the system. Okay, and you know, it is impossible for you to represent using a proper scale on the axis of a graph paper both the units in hertz and unit in megahertz. Okay, because there is a lot of power difference. And in order to accommodate that entire big range of frequencies, what do you do usually in your frequency response curve? On the x-axis, instead of representing or instead of taking the frequency of the signal, you usually go for taking logarithm of the frequency. And so that what happens is that the range of frequencies becomes what? Close. Not actually range of frequencies becoming close, actually the data getting what? Accumulated, or the data is getting converged. Okay, the first 10 is in the 1, the 10 to 100 hertz will be in the second T2. Okay, then 100 to 1000 kilohertz it will be coming in within log of 1000, that is 3. Then 10 kilohertz will be coming within 4. So you can see that the entire range of the frequencies will be getting converged to some numbers which you can easily manage. And remember, that is the sole reason why we take logarithms for large numbers here. And moreover, it is very easy to make calculations, especially in multiplication. You know, log of a into b is equal to what? Log a plus log b. So multiplication can be replaced with what? Addition. You know, addition is compared, and okay, division also can be just converted into what? Mere process of subtraction. Log a by b is equal to log a minus log b. So why do we go after logarithm of quantities in physics or mathematics? Basic idea is that is in order to simplify the calculations of calculations involving very big numbers. So big numbers can be just converged. So let me come back to my track. So what I was telling is that instead of expanding, Taylor expanding omega prime, okay, omega prime being a very large number, I'm instead doing the expansion of log of omega prime around er prime equal to e naught, or instead we can say that in place er is equal to 0. So let's see what will be the expansion. Okay, so I'm writing the expansion here. I think better I will just write what will be the Taylor expansion. I hope you remember still the Taylor expansion. We usually was having the Taylor expansion of a function f of x. Okay, so f of, you know, thus f of x, any function can be Taylor expanded around, say, some point, say a, around x equal to a. It will be just like f of a. That was a very simple expression that you have been using, Taylor series. Then we had to take the first derivative at x equal to a, which I am writing as f dash a, divided by 1 factorial into, okay, see, x minus a. I'm expanding it around a. Okay, right, plus what is that? F double dash a, the second derivative at the point x equal to a, about the equilibrium point, divided by 2 factorial, you know. Okay, so into x minus a the whole square plus like that, right? Now, so let's, therefore the same manner, so this is the reference, same manner, I'm expanding log of, I told you, log of omega prime, and this omega prime is a function of the energy of the reservoir, that is er prime, which is about which value? About the point e naught. Remember, we are expanding this one about the point e naught. Okay, or about the point er prime is equal to er prime equal to e naught. Er prime equal to e naught means er about the point er equal to 0. Same thing only. So I'm just making a Taylor expansion of the quantity about the point e naught. So it will be equal to, first one, f of a. F of a means about the equilibrium point a. So remember, a is equal to, with a is equal to e naught, I'm doing the expansion. A equal to e naught. So it will be equal to log of, log will be there, omega prime, log of omega prime at e naught as a function of e naught. Then plus, I should take f dash a. What is f dash a? F dash a is the derivative of f, okay, the function. So you know this f dash a is nothing but d by dx of f of x calculated at x equal to a. That's the meaning of f dash a in Taylor series expansion. So what I have to do, I take d by dx of, means I'll be taking, instead of say d by dx total derivative, I'll be preferring partial derivative, because you know omega is not only a function of er, it can be a function of what? Other quantities like n, v, etc. So I can say dou by dou er prime, dou by dou er prime. Just see that er prime is x, a equal to e naught and x equal to er prime. See that this okay, comparison is there always with your mind. So it will be dou by dou er prime of the function f of x. What is the function f of x? F of x is on the left side, that is log of log of omega prime er prime, that is my f of x here, and I should do this expansion at okay, now see, at x equal to a. So I am writing that is done at x equal to a. So I am writing it the denominator at er prime is equal to e naught. E naught is our x equal to a. So I have substituted for this f dash a divided by 1 factorial. 1 factorial is 1 into x minus a. Into x minus a. So what I have to do? So I have to just write into. So let me just rub the remaining thing for a while. So these things are understood, I think. Okay. So just multiplied by what is that? X minus a. So x is what? Er prime. Er prime is your x minus a is what? It's about the point e naught. So er prime minus what? E naught, right? Plus the second term, you know what will be the third term? It will be dou by, is not, okay, that will be 1 by 2 factorial into then dou square divided by dou er prime square of what? The same quantity. Likewise, so it plus it goes on. I'm just using only the first two terms. Of course, we will be neglecting the higher terms because of the very fundamental assumption that we have made. What's the assumption that we have made? Hope you remember, we have made the assumption that er by e naught is very small. Er by e naught is very small. Okay, what does it mean? It also means that if er is very small compared to e naught, or we can say that e naught minus, we can say that er prime minus e naught, that will be very small. Is it not correct? Because er, or we can say e naught is equal to er plus what? Er prime, that's the thing. Now you can see that this er is very small, this is very small. It means that e naught and er prime are very close, or er prime minus e naught will be very small. So since it is very small, what you can do is that you can neglect its higher powers. Okay, that's why we are neglecting the higher powers, or we are truncating the higher powers here. Now one more thing to proceed. What is this er prime minus e naught? What is this er prime minus e naught? So er prime minus e naught can be written, see for example here. So er prime minus e naught will be equal to minus of er from this equation, or equation number 1. Er prime, okay, so this is er prime, you take e naught here, so you take er here, so er becomes minus. So er prime minus e naught can be substituted as minus of er. So I'm just doing that. So that is the LHS is equal to, LHS is log of omega prime of er. So LHS is going to be equal to, or I can say roughly equal to, that is to be fair, roughly equal to, because I am doing one approximation by truncating the higher powers, that is equal to log of, simply log of omega prime e naught. I'm writing the first term as such, log of omega prime e naught. Then the second term, how do you write a second term? See, instead of this particular term in the bracket er prime in e naught, I am going to write minus er. And what is this dou by dou er prime of log of omega prime? Hope you remember from our discussion of first module that we have seen dou by dou e of log omega. Do you remember this quantity? We came across this quantity while we were discussing the thermal equilibrium. We discussed the 3 different kinds of equilibria. Okay, the thermal equilibrium, where we have seen statistically thermal equilibrium corresponds to the equality of beta 1 equal to beta 2. Okay, other one is what eta 1 equal to eta 2, and the third one, chemical equilibrium, is theta 1 equal to theta 2, where we defined beta as dou by dou e of log omega. So dou by dou e of log omega is nothing but the quantity beta, which is known otherwise as inverse temperature later. So here can't you see that dou by dou e, instead of e it is er prime, some energy, okay, which is a variable energy. So dou by dou er prime of log of omega prime. So this is nothing but the quantity beta. So what will be this one? So the second term is nothing but minus er multiplied with what? Beta. So I'm writing this one as minus. So this minus has come from this minus into beta. Beta is for the quantity, this entire quantity is beta. This entire quantity is beta. So beta into er. Okay, so I have on the left side, it is what? Log of omega prime er prime. That's right. Now just think of what is log of omega prime of E naught. You know, E naught is a constant, right? E naught is the total energy of the system plus reservoir. E naught is equal to a constant. Okay, so omega prime of E naught will be also equal to a constant. What is varying is okay, omega prime of ER or omega prime of ER prime. Both are varying because ER and ER prime can vary, but E naught is a constant by equation number 1. So I can say that log of this particular ER first term, so this one is going to be some constant. So that is a constant because it's a function of E naught. That's a constant. Minus, so it's a constant minus beta ER. It's a constant minus beta ER. Okay. So that is on the left side, it's omega prime ER prime. So what I can write is, if it is this one, therefore, this is log, of course, log of omega prime ER prime. That is a mathematical. Therefore, I can get rid of the log on the left side. So I can write that log of, okay, so instead of log, I'm writing, therefore, omega prime ER prime, omega prime ER prime. Remember, this is ER prime. That is okay, proportional to, I can say, because there is a constant that is proportional to so that is proportional to, it will be the constant I can get rid of. So e raised to minus beta ER. That is how we can just get rid of the logarithm. So you know that if log of say that x is equal to say some y, therefore x is equal to e raised to y. So I'm just using this simple thing, and I'm neglecting the constant because I have introduced the proportionality here. The constant will be included in the proportionality here, right? So but don't you remember what we have begun with? Why this omega prime ER prime? So in the beginning, very beginning, we have seen that the probability, we have seen that the probability PR is proportional to, okay, omega prime ER prime. So omega prime ER prime is proportional to the probability that the system is found in a state with what energy ER. So I can just rewrite that one with our quantity PR. So this is nothing but PR. So this is equivalent to writing PR is proportional to e raised to minus beta ER. See, is not the relation that we have been actually searching for, because our aim was to get a relationship between PR and ER. Okay, so remember what is the meaning of PR and ER. A system can have large number of energy occupancy, right? Because the system is in a member of canonical ensemble where the energy of the system can vary from 0 to E. So at any given time instant t, the probability that the system is found in a state with energy ER is what we call as what? PR. So that probability is what we have obtained. The relation PR is proportional to e raised to minus beta ER. Okay, so let me call this equation by some equation, say equation number 3, and let me proceed on and I think so. What is that? So that is, therefore, what we are able to conclude simply is that PR is proportional to e raised to minus beta ER. But we are not satisfied by just the proportionality. We want to make it an equality. Okay, so how can we do that equality? So what you can do is that I'm writing or I can write PR is equal to some constant C, let me call that as a constant C, into e raised to minus beta ER, where the value of that constant we have to evaluate. Okay, so in order to evaluate the value of the constant C, let's use the fundamental property of probabilities. What is the fundamental property of probabilities? You know that see the total probability, but sum over R, PR should be equal to 1. You know, yesterday I just the previous session we have just discussed that. What is that? If a system is having only 3 levels, I told you the example of a 3-level laser system. So having, say, energies E0, E1 and E2, and the probability that the system is found in a state with energy E0 is P0, and the system is found in a state with energy E1 is P1, and that with the energy E2 is what? P2. Now the system will be, or if you have some 100 particles, see the particles will be found either in say E0 or in E1 or in E2. Somewhere it has to be lying. So we can say that the total probability that is P0 plus P1 plus P2 should be equal to 1. It means that the system should be somewhere, right? The total probability. This is the same concept what we do in quantum mechanics, what normalization of the wave function. We make sure that no integral psi star psi d psi or d tau is equal to 1. What does it mean? We make sure that the particle is found somewhere in that region. Then only that is meaningful. So the probability that the system is found in any one of this state, the total probability that the system is found in any one of the possible state is always equal to 1. That's meaning sum over r PR equal to 1. So what is sum over r? So this is this same thing. For r equal to 0 to 2, this is something as what, like sum over r is equal to 0 to, let me say 0 to 2, PR is equal to 1. That is generally written as sum over r PR is equal to 1, right? Now that is the total probability. The total probability that the system is found in any one of the accessible state. Total probability should be equal to 1, right? That's the basic idea. And I can use this particular idea to calculate the value of the constant. How do you do that? That is sum over r. Instead of PR, I am substituting equation number 4. That is C e raised to minus beta ER. C e raised to minus beta ER, that should be equal to 1. I'm just substituting equation number equation number 4 instead of PR. That is equal to 1. Or you know that C is a constant which you can take outside. Or can you get C? What is C is equal to? C is nothing but equal to 1 divided by, what is remaining? Sum over R e raised to minus beta ER. That is C. So we say that this is some equation number 5. So you got the value of C. Therefore, what will be equation number 4 becoming? That's our ultimate aim. Therefore, equation number 4 gives you the probability PR is equal to e raised to minus beta ER divided by, say C, multiplying with the C, so it is 1 by. So that is divided by epsilon R of the same quantity, e raised to minus beta ER. And that is our ultimate equation we have been trying to derive finally. So this is the equation we are going to get. It's a very, very important equation in the entire canonical ensemble formalism, which we'll be using in problems which actually you are familiar, where you discussed population of states, etc. in spectroscopy classes or laser physics. I will tell you how to reach that equation later. So let me say that this is our equation that we were long searching for. Let me call it as equation number 6. And this equation, remember the denominator, the summation goes over all possible states accessible to system A, and equation 6 gives the probability that a particular microstate or eigenstate with energy ER is occupied, and the quantity in the denominator, which is evaluated over all accessible states. The quantity in the denominator, sum over R e raised to minus beta ER, is extremely important in statistical mechanics, and this quantity, the denominator of that probability equation, is usually represented by Z, or Patria prefers to call it as Qn of Vt. Q is the symbol and NVT is a subscript. Qn of Vt is called the canonical partition function. It is known as the canonical partition function. So maybe this is for the first time that you are coming across this term partition. Partition means dividing. Canonical partition function. That is the denominator of that equation 6, and see the term e raised to minus beta ER in the numerator is known as the Boltzmann's factor. So I'm just naming the quantities on that equation, being a very relevant one, Boltzmann factor. And this equation number 6 is called the famous Boltzmann's probability distribution equation. Boltzmann probability distribution equation, or it's also known as Gibbs canonical equation. Several names are for this equation that is that much relevant. Gibbs canonical distribution. It's a distribution of how particles will be distributed along different energy states, so it is known as distribution. So it's a Gibbs canonical distribution. So let me conclude this particular lecture here. we have a long way to discuss on equation number 6 and its denominator known as the canonical partition function, and we'll see that this equation serves as the opening into what is known as what the thermodynamics of system, as I told you in the very first lecture, that once you calculate PR using this equation number 6, you will be able to just dive into what is known as what the thermodynamics of the system. Okay, so keep reading so that you can understand it better. Thank you.